So welcome to this second presentation. The topic of this presentation is a hierarchical 3D design exploration mechanism that we have developed. Let me start by trying to acknowledge the complete team that has been working in this project. On the one side, we have the Georgia technology, led by Song-Kun Leung in the direction of EDA for 3D, also the support of IMEC, especially from Frankie Cator and Maurice Brunion in terms of the technology, then collaboration with the ETH Zurich, the group of Luca Benini regarding the mempool hardware, and finally our group at the University of Bremen working again in 3D design. Let me start with one short motivation. Let's consider that we want to implement a complex update system, like for example, the mempool. Mempool is composed in one of the constellations by 4 groups of 16 tiles. When we check what is in every group, you will see that this group is composed by 16 tiles of multi-core processors with some local interconnect, and then one additional connections in the north and the east with the other tiles. If we now zoom into the tile, you will see that the tile is a complex 4-core system with L0 cache, L1 cache, interconnect, shared memory, and so on and so forth. If we want to implement this system in 2D, probably we will subdivide it in small blocks, and we will independently synthesize and perform the physical implementation of the different subblocks in a hierarchical way. Once we have implemented, for example, the tile, we will integrate the tile into the group, and finally we will integrate the group into the final system. We just traverse the hierarchy from the bottom to the top. This methodology is perfectly well established in 2D. However, when we want to implement such a complex system in 3D, we will find dramatical difficulties. So fundamentally, the goal of this short seminar is just to introduce one mechanism to allow to use 3D physical implementation in this scenario. But let me first review which are the benefits and the difficulties of this hierarchical approach. In terms of the benefits, we see that we can address very large designs, like for example, the mempool that we have discussed before, with an acceptable runtime, even if we have system with maybe 128 cores. We can reuse identical blocks. This was completely clear in the previous example, where we have a multi-core example. Also, in commercial environment, it is of great importance that we can concurrent work with different teams, with different persons in the same project. So maybe we have some implementation in the NOC, another one in the course, and so on. And finally, another big advantage of the hierarchical methodology is that we can elegantly implement third-party intellectual property blocks. All these 4 aspects play a key role, especially when we want to do an easy design exploration. If we want to see what happens when you change the number of tiles that we have in the group, for example, or if we change the area, which are the implications in the final layout. However, this hierarchical approach has 2 fundamental problems. The first one is that we require a careful budgeting of the different blocks, especially in terms of timing constraints. And second, that we also have to define very precisely the physical constraints for the different hierarchical parts. In the domain of 2D, we have some tools which are helping us in this regard, but again, in 3D, there is almost no tool for doing this. In the next slide, I would like to summarize which is the state of the art in terms of flows for 3D. Fundamentally, the 2 more, let's say, important ones are sequential 2D and macro 3D. And what we would like to present today, we want to discuss today, is a new hierarchical 3D flow. The key idea of the sequential 2D is basically to use a partition so that we can implement our design in two separate dies which are separated. In macro 3D, the key idea is that we can try to implement a system using a memory on logic approach, but using a holistic view so that we can see the complete metal stack. These two methodologies present some advantages and disadvantages. For example, in terms of sequential 2D, the fact that we can have a very free partitioning is a very plus, while it has some negative aspects, like, for example, that we need to perform a partition, which typically is very, very difficult to do at the first. On the other hand, macro 3D has some advantages in terms of using all the, let's say, possibilities of the routing simultaneously in the three dies, while it has some limitations since it is mainly focused in memory and logic. What we would like to do is to try to combine the advantages of every one of these approaches so that we can get no restrictions in terms of the partitioning, that we can get a holistic routing approach like in memory 3D, and that we can also use the space that we have in the different dies to the maximum. Before we start with the explanation, let me try to summarize again these strengths and limitations of the existing flows. As I said, one of the strengths of the sequential 2D approach, what you can find today in Cadence, is that we have no restriction for the partitioning that provides a high flexibility. However, we need the critical partitioning step, a complex modeling of timing constraints, and probably the key problem is that when we are routing, we cannot reuse the backend of line of the different tiers at the same time. If now we compare that with macro 3D, you will see that the fundamental strength is that we have a complete view of the timing constraints and the bucket of line so that we can use metal. In this sense, we can provide a full pleasant route with a complete optimization using, for example, incremental synthesis while the pleasant route. However, we have two important limitations. First is that this approach is limited to cases where we have large IPs, like, for example, when we are working with memory on logic. And also that it is very common, if the two tiers are not perfectly 50%, that some area in some of the tiers will be waste. Our solution for that is hierarchical 3D flow. In order to understand hierarchical 3D, I think it will be worthy first to have a look to the macro 3D overview. Here you have, in a short slide, hopefully you can see it, the key idea of macro 3D. On the right side, you see which are the elements that we need to be able to execute these in terms of the creation of a full pattern of line and the creation of IPs. In the left side, you can see the steps. Fundamentally, if we make a zoom, if we try to have a look about which are the requirements, you will see that the fundamental idea of macro 3D is that we start with two separate tiers and we want to combine them into a single full stack backend of line. These, for example, can be done combining the left files of the two technologies, allows the tool simultaneously to have a look to the complete stack. Yeah. If we make a zoom to the second part, you will see that when we are doing the routing, in fact, we can combine metallization between these two tiers. The next step that we need to execute this flow is the generation of dedicated IPs. If we, for example, think in terms of the implementation of memory elements in the top tier, you will see that by implementing there, the location of the pins is not going to be in the original metal 3, but in another layer according to the F2F full build. This is what we call here M3MD. So we need one step where we adapt all the IPs that we are going to use into the, let's say, die where they belong. Good. So here you have seen these two parts, creation, full by all, and create the IP. If now we move to the right side, so the steps, the fundamental steps that we have is first the floor planning, where we try to define what should go to the top die, what should go to the second one. Then we have the 2D projection step, where we project the pins of the top die into the lower one. Then the next step is the complete place and route and sign off of the bottom tier, just using a standard 2D methodologies. And finally, when we have this place and route, we can proceed with the last step, where we have to separate the combined stacks into two, so that we have the top tier and the bottom tier independently. Again, let me have a look to this step with more detail. Here we have the step corresponding to the floor plan. You can see that when we are working in the bottom die, we can locate some macros with the normal pins without any restriction. When we are locating macros in the top die, this macro we leave in the additional left tiers that we have developed before, while the pins are going to be projected. Here you see this small red square from the top tier to the bottom tier. Once we have this substrate, you notice that to make sure that the tool can understand that, the trick that we are going to use is to have one virtual macro that occupies fundamentally the size of a standard cell and that has pins projected into the place where actually belong to the lag macro. Once we have this system, we can proceed to the normal place and route. Observe that in this step, the complete place and route is done completely with a standard 2D tools. The tool sees the complete stack of metals because we have extended LF files. The tool can change the location and the size of the standard cells. We can floor planning automatically all the macros that we have in the lower part. The only limitation that we have is that the location of the macros which are in the upper part is fixed. The two advantages that you get with that is that we have a perfect definition of the timing, and also that we can use the complete stack for the metallization even if we are using a standard 2D tool. With this idea in mind, now we can try to address how can we extend this macro 3D tool to cover more complex scenarios. The fundamental idea is to try to combine the advantages of sequential 3D in terms of floor planning, freedom for the partition, and macro 3D in terms of seeing the complete style flow. And for that, what we are going to use is a bottom-up hierarchical approach where we decompose our implementation problem in different cycles of iterations. Probably it is easier to see that if we have a look at a concrete example. Let's imagine that again we want to implement the mempool. So the first thing that we are going to do is to define our hierarchy, our steps. In this case, they are pretty clear just by the definition of the hierarchy in the design. So we have the tile, the group, and then the complete system with the 4 groups. Then we start with implementation of the core. This is what you see in the small graph in the upper part, in the small image in the upper part. Here we have used an approach similar to macro 3D, where we have decided to place the large L1 cache in the top tier, while in the bottom tier we are placing the standard logic cells for the design, but also the 4 L0 macros. Note that since the system is asymmetric, so the area of the bottom tier is larger, we are reserving some area in the top tier that we will reclaim in the following iterations. Also, you see that there is a couple of small green points. These are some areas that we are reserving already so that later on the implementation of the system is easier in following iterations. Once we have this partition with this step reserved, we can use the normal flow that we have seen before to complete the tile. Once we have the tile, we can create the group. For that, conceptually, we just have to integrate these 16 tiles and to add the logic for the log interconnect and for the node. Note that we can do this just by swapping the concept of what is the working tier, what is the tier where it's fixed, so that in this iteration, the complete tile is seen as an IP, only occupying the part where the standard cells and the L1 memory is located. In this iteration, all the blue areas that actually are in the top tier will be used for routing, for generating the local interconnects and the logic of the group. Just a small detail, even if right now we are working in the top tier, because the tools need to see the stack in the proper way, actually what we are doing is to flip everything so that the tool believes that the top tier is actually the only tier where we have standard cells. Again, there is some asymmetry between the top and the bottom tier so that we have one space that we can reserve for the next iteration. In the next iteration, we just connect the different groups together, and now our design is fundamentally similar, our flow is fundamentally similar to the macro 3D, where again, we are just placing the standard cells in the bottom tier in the regions which are in green. Notice that when we are in this step, there are some areas that we reserve already in the tile with green areas that it can be reused right now. This allows a great flexibility in terms of the location of the buffers when we are generating the complete system. You see that the fundamental idea is that we are doing a kind of partitioning, and that in each iteration, we are just using the full methodology of macro 3D. In the next slide, I'm showing with a bit more detail exactly how the procedure is working. I think we just have a couple of minutes, so let me go relatively fast on that. What you show in the left is actually the location of the top and bottom tiers, for example, when we are working in the first step. You see that in the bottom tiers, we have our standard rows for cells. We are placing in one cell, which actually is the size of our standard cells, but that represents the complete memory that is going to be located in the upper layer. As we place this element, the pins of the memory are propagated to the bottom tier. These are the yellow elements that you see there. In addition to that, you see that we need to define some blue pins. These are the connections of the tiers with the next levels. And finally, you can also see in gray that we are reserving some space that can be used for the different elements. Once we have defined this flow plan, we can just run the normal methodology. And as you can see in the section in the middle, we can do the normal routing. We just see additional vias in the F2F layer, and we can just use all the meta layers in our design, both the layers that we have in the bottom tier, but also the layers that we have in the top tier. The tool realized that he needs to do a connection to the memory macro. Even if he does not see the memory macro per se, he just sees one abstraction. Once we have done the implementation of this part and we go to the next iteration, then we have to work on the top tier. And I said, this is the point where we have to do the stack inversion. We just rename what is the metal 1, metal 2, what is the standard cells in such a way that now the place and route tools believe that he's just working in one of the tiers. Note that when we do that, we have to change automatically all the interconnects that we have done before into abstractions. We have to replace the location of the memory macro with one overlap and one construction. And after doing that, we can proceed with the normal place and route. By iterating with this stack inversion in different layers, we can complete the implementation of our chip. Yeah. So summarizing, you see that fundamentally what we are using is a bottom-up hierarchical implementation approach. where we are reusing the assigned area that we have reserved so that we can minimize our constraints. We are working fundamentally in a multi-tier approach, and because of this ping-pong approach between the different tiers, we can in fact place cells in both dies. This greatly expands the possibilities for 3D design and also the design exploration. If we want to implement completely that, let's say, the rough idea that I described right now, you see that some of the elements that we need is first a RTL clustering approach in such a way that we can cut our design in different steps. We want a logic-on-logic floor planning approach that we have to do at the very beginning. And also, we require a holistic approach for the 3D physical implementation that we are implementing using Macro 3D. In order to enhance the methodology, it is also possible to add one automatic floor planning step, and also it's possible to add some improvement in terms of the definition of what is white space, so that we can get a trade-off between the possibilities of recovering the space that we have in different iterations without having to create a much detailed left file. This slide, you have the complete flow that we have in hierarchical 3D. You just see that we start with hierarchical partitioning, then we can start with implementation of every block, then we do the 2D synthesis using the standard PDK with the additional definition of methodologies and the IPs with extension. Then we can do the 3D floor planning with budgeting, placement, and legalization. Out of that, we generate the complete 3D netlist, and we can do the full place and route. Once we have seen one iteration, we can abstract this step, generating a detailed left and lib file of our block. Then we feedback to the stacking version, we change the design, and we continue iterating. Once we have completed all the iterations, we can just proceed with the full chip assembly and the final GDS. I said there are two steps that can be used to enhance this approach. The first one is the clustering approach. Basically, what we are doing here is to analyze our netlist and to try to see which are the different blocks that we can combine into one single cluster in such a way that the floor plan later on and the distribution between the different tiers is even easier. Fundamentally, this is a clustering approach. I think it's not worth it to go exactly to the details of the algorithm. The second enhancement is actually the automated floor planning. Shortly, what we are doing is first we start with a Fiducia-Matthews partitioning, where we cut the netlist into different parts which are related with what we want to place in the bottom and the tier. With this initial partitioning, we fix it, and then we start to analyze the assignment into the 3D part using just a 3D sequence per generation. These steps are very similar to the steps that you will find in any sequential 2D methodology. After doing that, we will unfix the partitioning, and then we will start a simulating annealing approach, where we try to improve the location of the elements and the macro. After this initial simulating annealing approach, we will fix the macros and the outlines, and then we will continue with another simulated annealing, where we try to determine the complete location of the elements. Once we have the floor plan, we can automatically perform some assignment of the vertical interconnects of the MIVs, or the face-to-face interconnect to the layer. And for doing that, fundamentally, what we are using is assignment that try to minimize the distance using a bipartition approach. In the cases where we are using face-to-face approaches with a large path, it is normally require a legalization approach and to keep out of zone distances so that we have few violations. In this slide, we just have a summary of the result. Here we are comparing for mempool, actually for the full cluster, which are the results that you can get with 2D, with the sequential 3D, with macro 3D, and with a hierarchical. You see first that obviously macro 3D have some advantages versus sequential 2D because of the possibilities of a perfect location of the macros, but nevertheless it weighs some area that actually is recovered by hierarchical 3D, so that we can get an area 0.65 that is dramatically smaller than what you will get with sequential 2D or macro 3D. Also, because of the clever use of area, you see that actually we get a huge improvement in terms of the effective frequency. In particular, in the cluster, we have a high density of interconnects that were limiting the speed of the system. And by reducing the space that we have between the tiles, you can see that we can get a much better result. So that finally the die cost is much smaller, and also we get a power delay performance which is almost double what you could get with other methodologies. In this slide, you can see just graphically the result of the place and route of the mempool. Here you have the 2D approach with the tiles, and you see that there is quite a lot of congested area. Then the results that you will get with the sequential 2D or macro 3D, they are quite similar. You can see that we have tiles in the bottom and memories in the top. You can see that because of the use of the macro 3D approach, most of the top tile is completely unused, and because of that, we have a higher area and more congestion in the bottom tile. And finally, in the lower part of the slide, you can see the bottom and top tiers with the hierarchical 3 methodology, where you can see that the tiles are placed much close, and how in the top tier, there is actually a lot of cells which are used for doing the connection, and because of that, we can reduce the area and improve timing. We have repeat experiments with Cortex, where we have 4 cores with an L2, and again, you can observe the same results. We can also analyze GPU like the Mali G52, again, 2 different cores, logic in the bottom and the top, the results are the same. By using this hierarchical methodology, we can get huge improvement. So with this, maybe I can conclude. Fundamentally, what we have presented is just the possibility of doing a full chip R2L2 GDS physical implementation using a hierarchical approach for 3D that is able to exploit the hierarchy that we have in our design. It is based on the idea of cutting our design from bottom to top, where we are reusing all the unsigned area and exploiting all the tiers that we have. With this, I can conclude this small part of my presentation, so thank you very much for the attention.